In this tutorial, we are going to solve a problem on fluid statics on curved surfaces. This problem is taken from Yunus H. Engel and John M. Simbala, Fluid Mechanics Fundamentals and Applications, 3rd edition, problem number 3-68E. The original problem is given in imperial system. For convenience, all data given in imperial units are converted to SI units. A long solid cylinder of radius 0.61 meter, hinged at point A, is used as an automatic gate as shown in the figure below. When the water level reaches 4.57 meters, the cylindrical gate opens by turning about the hinge at point A. Determine A. The hydrostatic force acting on the cylinder and its line of action when the gate opens, and B. The weight of the cylinder per meter length of the cylinder. Let's consider a block of liquid below the cylinder. Let's take a look at it closely. Let's see what forces are present on this block of liquid. Firstly, the weight of the fluid block, which is the product of its volume with the mass density ρ and the gravitational acceleration g. The volume of the block is this area times the width of the gate. Let's take an assumption. The width of the gate is not given in the problem. Let's assume it to be 1 meter. Later, the results obtained will be per meter width of the gate. This area is nothing else the area of this square minus the area of a quarter circle. After putting the known values, we obtain 0.08 meter square. The width of the gate is 1 meter. Hence, the volume of the block is 0.08 meter cubed. Multiplying this volume with ρ and g, we obtain the weight of the fluid blocks, 784.8 Newton. Now, let's take a look at the base of the fluid block. The pressure distribution at the base of the fluid block is uniform. It is caused by the depth of water, which is 4.57 meters. This pressure distribution creates a resultant force Fy equals to ρgHa. Here we take an assumption that atmospheric pressure acts on both sides of the gate and thus it can be ignored. The area at the base of the fluid block is 0.61 meters times 1 meter. It gives 0.61 meters square. Putting all the values in the equation, we obtain Fy equals to 27,347.34 Newton or 27.35 kilonewton. Now let's consider the vertical surface of the fluid block. The resultant force Fx equals to rho times g times h centroid times A, where the centroid is in the middle of the vertical surface. It equals 4.265 meters. The area A, which is the area of the vertical surface, is 0.61 meter times 1 meter. It gives 0.61 meter square. Now, putting all the values in the equation of Fx, we obtain Fx equals to 25,522.17 Newton or 25.52 kilonewton. Now we draw the reaction force from the gate to the fluid, which is Fr. Its horizontal component is Fh. And its vertical component is Fv. All these forces constitute the free body diagram of the fluid block. The fluid block is in equilibrium, so we can apply the equation of equilibrium in x and y direction. In the x direction, we have Fx minus Fh equal to 0. This gives Fh equal to Fx, which is 25,522.17 Newton or 25.52 kilonewton. In the y direction, we have Fy minus W minus Fv equals to 0, or Fv equals Fy minus W. Putting the necessary values in the equation, we obtain Fv equals to 26,562.54 Newton or 26.56 kilonewton. The resultant force Fr is obtained by calculating the square root of Fh square plus Fv square, and it gives Fr equals 36,836.80 Newton or 36.84 kilonewton. The angle theta, which is formed by Fr with the horizontal, is calculated using tangent theta, which is Fv over Fh. We obtain theta equals 46.14 degrees. The resultant force Fr obtained previously is the reaction from the gate to the fluid block. The force from the fluid block to the gate is the same in magnitude with Fr, but in opposite direction. Now let's draw the free body diagram of the gate. The weight of the gate is W seal passing through the center of the cylinder. Here we assume that the material of the gate is uniform. At the hinge A, we have the reaction force AX and AY. We assume there is no friction at the hinge A. At B, at the bottom of the gate, the reaction is BY. Note that when the gate starts to open, the reaction at B becomes zero. This is the free body diagram of the cylindrical gate. Applying equilibrium of moment of the gate about point A, we have Fr times AD minus W seal times AO equals 0. AD is R sine theta. AO is R. Putting all values that we have in the equation, we obtain the weight of the cylinder equals 26,560.62 Newton or 26.56 kilonewton. Let's summarize. The first question is, we need to determine the hydrostatic force acting on the cylinder and its line of action when the gate opens. We obtain the hydrostatic force Fr equals 36,836.80 Newton or 36.84 kilonewton. Its line of action forms an angle of 46.14 degrees with horizontal. The second question is about the weight of the cylinder per meter length of the cylinder. We obtain the weight of the cylinder equals 26,560.62 Newton or 26.56 kilonewton. With this, we solve the problem.